We're going to do an example in chapter 6, number 2, which is really a simulation experiment to help you understand how the spread from sample average to sample average changes as a function of the sample size. Let's share the whole screen. Let's find the problem. So the problem, again, in chapter 6, number 2, gives you random numbers chosen between 0 and 10. And we will learn later on when we do some simulations at the end of the class how to do that. You say something like ran between, and you pick, the computer picks a number between 0 and 10. But they do it not just once, they do it 50 times, and they give you a whole list of numbers, as we'll see in a second. Let's see the numbers in Excel. Oh boy, okay, this doesn't seem to work. We have to start from scratch again. Get rid of that, go to here, go to the chapter 6, number 2, click on the student's problem. Let's show completed, which gives you the answers already plugged in so we don't have to redo them. Let's pick the numbers that were chosen here in Excel, in the data file. And we see here that the numbers were chosen, the first, which 2.83. You would think, there's no particular bump in the data. It's uniformly distributed. It's somewhere between 0 and 10. It could be just as likely to be a 1 as it is to be a 9 or a 3 or a 4 or a 5. Of course, the average is 5 because that's right in the middle between 0 and 10. So the numbers above 5 and below 5 should cancel out. So let's, first of all, get the average of the averages. I'm doing this because I had a problem before. I want to make sure that this is going to be, I'm going to write this here as the grand average of all, 50 times 8, 400 numbers. Put that in this box here. Equals the average of all these numbers. Just going to want to verify that we're getting the same answer as the book, or using the same numbers at least. And 5.016. And what does the book say? The 5.016. We're good. Okay. So let's continue this now. Let's get rid of the other ones, which we just used for me as experimental. Okay, don't save. So we're back to this one here. So the grand average is in fact the same as the books. Now you'd expect it to be very close to 5 because the ideal number is between 0 and 10 is 5. Okay, but that's not what they really want right now. They want you to get the mean, the actual mean of each column. Let's call it the actual. And that's done by getting the average of the first column. You'll see why we're doing this in a, let's go from here to here. And we can hit enter. So the first average is very close, a little bit lower than 4.5. The actual standard deviation. Is that a question we really wanted to answer? Standard deviation of 8 sample means. No, we don't need the standard deviation, but let's do it anyway. I'll tell you why it's going to be interesting. You want the actual standard deviation of these 50 numbers, and that's done by typing in STD. Look at the equal sign, STD. We want the sample standard deviation, and we want the values from B1 through column to B51. Enter, and this comes out to 2.69. Now comes the theoretical Now, this is based on random numbers, so each time you do it, you're gonna get a different answer. What is the theoretical standard deviation? Well, better yet, what's the theoretical mean? Well, that gotta be the number, equals 10 plus 0 divided by 10 plus 0 divided by 2, or you should really say 0 plus 10 divided by 2. That should come out to 5, as common sense would dictate. What's the theoretical? Theo, I spelled it wrong. Theoretical mean. And what is the theoretical? We'll need this theoretical standard deviation. That's gotten by taking the equal parenthesis, the top number minus the bottom number squared of the 6 squared, that's how you square something, divided by 12. See what happens. All right, what am I doing wrong here? We want the square root of 10 minus 0 squared divided by 12. We don't want the square root there. Let's see. See if that works out. No. 4. What's happening? The square root of the answer is around 2.8. I made a mistake here. Square root of minus 0 squared is 100 squared. I mean, it's 10 squared or 100 divided by 12 is around 8.33. The square root of 8.33 is about 2.8 something. You're wrong. With the square root of the square root sign goes outside of the 12. That's the first one mistake. So we have another parenthesis here. Now that should work. Yes, 2.88 is very close. In fact, it got to be close to the actual standard deviation, 267, 288. All right, let's repeat this now for all 5 of them. So we see again, these numbers are pretty close to 5, as you would expect. The averages of 50 numbers. And then the standard deviations are close to the ideal, 2.88, a little bit lower, a little bit lower, a little bit lower, a little bit lower, a little bit higher, a little bit higher, a little bit. They should be pretty close to this ideal number of 2.88. Now, then we have one more concept called the standard error of the mean, which is, well, I'll just refer to the fact that it's up here. Here, the standard error of the mean, and that's equal to the theoretical standard deviation, which we just know is equal to B55, divided by the square root of the sample size, which in this case was 50. Left out an equal sign, so we have to mix that up. And this comes out to 0.4042, which we'll hopefully verify in a second, 4082. Oops. 4082. And I'll talk a little bit about this, but again, the videos really that I made on this chapter really explain this in much more detail, and you'll be working with this in later simulations as well. So what do we have here? So one more calculation is necessary. What is the spread among these averages? So again, we have a bunch of averages. We calculated the average of the averages, which we haven't done yet, because they ask you for that, equals the average of B52, which is the first average, through I52, which is the eighth average. 5 point, and this average of the averages should be equal to the grand average 5.01651. So far so good. But now comes the most subtle part of this thing here. They want you to calculate the spread among the averages. I'm sorry, I should have put this. I should have labeled this. Well, we could put it over here. This is equal to the average of the averages. What about the spread? Because when we're dealing out calculations, we like to know, well, how likely it is for a particular average to be above or below the ideal average. We need that for hypothesis testing. We need that for probability, which is used in the hypothesis testing. We need it for the confidence interval. So we want the spread among the 8 averages. Well, many ways to measure spread, the range, the high minus the low, but we've been doing it, the most basic way is by the standard deviation of the sample. What the sample is, in this case, a bunch of averages, 8 averages. So it's going to be B52 through Y52, and that comes out to 0.368887, very close to the theoretical standard error of the mean. So again, what the standard error of the mean is predicting for us, without having to go through this whole rigmarole, is that when data is coming in randomly, in fact, 50 of them, where the amount of spread between 0 and 10 is quantified as 2.88. If you take 2.88 divided by 5, you get 0.40. That's the theoretical spread from average to average. And you can see that it jumps from the ideal 5 by about 0.40. That's what it's saying. And we're not getting, again, this is random, so it's going to be a little bit different in the theory. But in this case, 0.37 is pretty close to 0.40 when you round it. Okay, so let's just see how close we are to the actual numbers without having to retype them. So we have 3689 is the spread among the 50 averages. The standard error is 0.40. The average of the averages is 0.5. So all these numbers are working out. Now they want you to repeat this again for 100, 250, and 500. I'm going to let you do that on your own. It just means extending this, looking at the data and taking bigger averages. But what you're supposed to understand, what you're supposed to demonstrate from this, as the sample size gets larger and larger, this formula will go from 50 to 100 to 250 to 500. So with this number, the denominator is getting much bigger. So the spread will get smaller and smaller, which means what you get is just common sense that as your sample size gets larger, they get more accurate. If they're more accurate, each of these numbers will be based on, let's say, 500 numbers, will be very, very close to 5.00. So there will be very little spread among them. And in fact, the spread would be 0.12 if you plug this formula, instead of dividing by 50, you divide it by a 500. Let's just do that right now. 0.129099, 1291 really. Okay, so that's enough for that. Please, let's get back to some more theory. So basically what they want you to notice is that the sample means are closer together when around the true value of 5 as the sample size increases. This is off by 0.01. By the way, we're not really seeing that. That's actually not, that's the right answer, but it's not what's happening in the data because it's random. This is off by only 0.01. A larger sample size is off by 0.04. You'd expect it to be off by a smaller amount. The next number, a really large sample size, is off by 0.06. The giant sample size is off by hardly anything. So that's, but this is not really a cluster together as the sample size increases, is not what we're seeing, but that's true theoretically, that's the right answer. That's not true. That's not true. It's the opposite. No, This is the right answer. Now comes the last part of this, which is really to show you, asking you to remind you to use the empirical rule. The empirical rule says if you take the average of any set of data and add the standard deviation of that data 3 times, you'll get an upper limit that's going to contain 95% of the data. So for a sample size of 50, let's take the average, go back to the Excel. We're not finished yet. We're going to take, I think, let's go back to this number. We changed it from 50. Let's make it accurate for this particular example. Let's take the actual average, which was, see, what are they trying to do? For the grand average? Or the, let's see it. With 3 standard deviations. All right, this is the standard deviation among the averages. And this is the averages among the averages. So if you take this number here, 5.01, and add on 3 spreads, 36 plus 36 plus 0.36, let's do that. So this is going to be the upper limit of the empirical rule. And let's make it easier to read. And it's equal to the average, which was found in column J52, plus 3 times asterisk the standard error, which is found in J53. Oh, just type, it worked. Yeah, 53. All right, oh, try it again. J52 plus 3 times J53, and it comes out to 6.1227. Let's see how close we are. 6.11. So how close, what do we say? Is that rounded? 6.11? Yeah, well, we're off by a little bit. We still mark it right, I believe. I'm not sure why this happened. Maybe they're using a different average. Let's try the lower one. The lower limit of the empirical rule is you subtract equals the grand average, which we said is 5.016, which is in column J52, minus 3 times the standard deviation among the averages, which is J53. Enter. 3.90. And how is it? 3.89, or off by a little bit. That's annoying, and I'm not sure what's happening here. It's still been marked right. So you're allowed a 0.10 leeway. And that's how you do it for 50. I'll see what the right answer is. That's the right answer. Taking the grand average, 5.0162, adding 5.0162. Let's see what they have here. What we have here, 5.0162, 5.0162. I use a slightly lower number. Maybe they're rounding it. And they use for a standard error 3. I used 3.9. I used 3.3688. They use 0.3. They use. Let's use the rounded numbers. Okay, let's do it. I'm going to do this on a calculator. Going to take. Let's see this. Sorry for the delay, but live and learn. 0.3689. 3689 times 3 equals, add to that 5.0162. 5.0162 equals 61229. 612. No, same number I got. I'm not sure where they're getting their average. Maybe they're using, well, let's see, let's compare the answers. 6 point minus the book's answer of 6.11, 0.0129, 0129. Maybe they're using the ideal number of 5. It's the only thing I can think of. Anyway, if that's the case, the book would be wrong. It should be using the theoretical, the actual average, not the theoretical average. Okay, so again, I'm sorry for the slight confusion. I believe the computer would mark you right because again, if you put down 3.89 and it's really 3.90, again, what did I say? It will be marked right, as long as it's within 0.10, which is a lot of leeway. Plus or minus 0.01. Well, 3.90 would be marked as well. All right, I'm going to, at this point, rate of show completed. Let's pick another example. Okay, I'm going to put in wrong numbers here. Just to get another example, I don't leave you with hanging. These will be wrong, obviously. As the sample size increases, the error decreases. That's common sense, and that's what we've been seeing. Okay, our answer is wrong, but check answer, final check. Okay, let's hear a similar question. The decrease part is right. Similar question. Let's see how the book does it. Do an example. Okay, they start off with the formula. They tell you to take the data, copy it into Excel, get the averages, pull over the averages. We're getting through this quickly because we did this in detail before. We got that 4082 again. This is the average. Ideally, it's going to be 5. They continue, spread here. To fill it in. Show completed. Let's go back. What just happened? To go through that example. I'm sorry, again, taking this too long. You can fast forward through it. I want to figure out why we're getting a small discrepancy. Let's try this. Maybe the book, maybe I didn't notice what the book says is the way to do it. They usually give you a formula they want you to use. Oh, the population mean. Not sure if they're doing this correctly. I think they're using the ideal value of 5. Let's try that. If you take standard error, we have it here. Point. We have to look at an example. Check answer. Okay. Final check. Okay. Similar question. I'm sorry, we were doing this before. I'll give an example. So one more time, continue, 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 continue. This is that same. Now they give you all the relevant data. Okay, so now they want you to calculate the ideal value. Repeating this now for other. Okay, for example, okay, so they are using the theoretical numbers, and that is incorrect. But all right, let me. They're saying that you'd expect 95% of the averages. All right, so let's follow this. Instead of using what I thought we should be using is the ideal numbers. I'm sorry, the actual numbers. They're using that theoretical 4.082. Oh, sorry, 4.063. Where'd that come from? Oh, there it is. They're using a combination. That's what's screwing. It's really screwed up. Using the actual standard deviation among the means, called the standard error of the means, which we calculated before. Doing 3 of those, added to the ideal number of 5, and then subtracted. So if we do that, well, we're pretty sure to get the same thing they just got, which was 4.36 on the low side, 5.64. So getting back to our problem, we should have done in this formula is not J52, but simply the number 5, which is found here, by the way. I could have put it here, but it's a 5 plus 3 times J53. So by now we don't know what the answer is, I don't think. So the upper number is 6.10. Is that what we saw before? And what's the lower number? I'm going to change that to, again, not the cell, but the ideal value. 3. Yes, these are the numbers I believe we saw before. 6.11 when you round it off, and 3.89. So a little bit long, but hopefully worth it. And again, you have to repeat that same thing for 100, 100, 250, and 500. But the main point is that the spread from average to average depends upon 2 things. It depends upon the spread among the original numbers. In this case, we're going between 0 and 10, and it has a spread of 2.83. And also, as common sense would dictate, it depends upon the sample size. If you have a very large sample size, so every average is very similar to every other random average, there'll be very little spread from average to average. Okay, that's it, folks.